So good afternoon to you all. I hope that all of you are doing well. So in today's basically we are starting the module on introductions to AI for EO. So in this module we'll try to spend more time on working of the different models and trying to build some example applications. So that's the basic focus of this whole module. And in between we'll be having a few basic lectures. We won't be dealing much on detailed explanation of the different models which is available for different AI based task which we are going to have. So instead of that, we'll be spending more time on working of taking the data sets and working on that. So today is just introductions of to give the flavor of what are the different tasks which we can do it in AI framework. And next class onwards, we'll be seeing a few examples of them in coming modules. Next, we'll be also implementing a few of the basic examples of CNN and DNN based models, and we'll also see the example how we can execute it in a real-time environment. So that's the basic structure of this whole course. So, and we are having a one-day basic lectures, and next day we'll be having a detailed demonstration of lab-based exercises. So we expect that all the participants may be actively involved into basically on the working of different models, how it gets executed. So they should be prepared with downloaded data sets and corresponding environment so that they can compute and get any clarification which may be required during the lecture time. Okay, so if you see in case of Earth observations, so there are multiple tasks which is required to be identified. So we are just listing 4 of them, but there are other tasks as well. In all these tasks like image classification, image segmentations, building the topological relationship, especially related to spatial data sets, then based on the temporal data sets which we can identify the trend of particular place, like is the place is a commercial one or it's basically a residential areas, we can identify that. Along with that, we can also identify different phases of the vegetation cycle. Those are called actually phenology. So that's also we can extract it from the temporal resolutions. So to carry out those tasks, we need to have a few subtasks. So mostly the data preparation sections where we need to prepare a few data sets, because satellite imageries are actually having a multi-dimensional data set. So we need to have a few understanding and how we can read it and process the satellite-based data set in our computing environment so that we can use it for different ML tasks. So we need to understand that how we can do that. So we'll also have a demonstration how to read the different raster data formats or the vector data formats, and then we can also create a few augmentation data sets. So those are basically the 2 stages of input data preparations. Then we need to have a basically database training. So there are a lot of different algorithms which basically relates to the finding out the deviation of actual data sets result and corresponding model predicted output. So based on that, it tries to minimize the error, and accordingly the updations takes place. So that's basically the case of learning based algorithms. So there are forward and backward algorithms which we will see during the implementations. And then after the carrying out the different steps of AI based task, what we will be doing is we will be doing that evaluations, that is the different steps which has been followed is actually effective enough. So there are a few measures. So those measures can be used for creating the data sets and evaluating the basically the output of the different models. Then how to implement it? So we may be implementing it or we'll be having a few demonstrations on basically Python based platforms. So this will maybe a TensorFlow or maybe a PyTorch. So we'll be demonstrating that as well. So this is the different task which we can carry out within, under this module. So EO datasets or the Earth observation datasets basically deals with two major categories. So some of you who are familiar with GIS may be aware of that. That's called vector data and raster data. But the people who are not from the remote sensing background, so this for them it's basically a way to represent the spatial data sets. So like there are two ways of representing the spatial data sets. One is that you can represent the spatial data sets in a vector form. So vector form, basically what you do is you mark different points, like for example a road. So road can be considered to be a connection of multiple segments, or those segments are actually connected with each other, and that forms the road. So generally in that case we create points at different geographical locations, and then we understand that there might be an edges between 2 points. So physically there may not be any entry for the line, but that can be stored as a tuple or as a pair of points, start and end points. So that way we can create a vector-based data sets. So these vector-based data sets can be used for object-based analysis. So generally what we do is we create these vector lines to delineate the features from other surrounding areas. For example, in a satellite imagery, we can see that a particular place is actually a park, or maybe some kind of parking areas, or it may be a stadium. So we will be having an outer boundary which can depict that within the content of that boundaries we are having an object. So that can be represented with the help of vectors. So generally in vector data we'll be having 3 different categories. One is the point, so it's basically having a geospatial locations and corresponding features. So that's what we are having it in form of vectors, points. In the line we'll be having a connectivity between different points, and area is basically nothing but a kind of line which is closed. So it means start and end point in the area has to be same point. So when any particular line, if it gets connected, then start and end point of that line, if it is same, then we can call it that this is basically a vector area format, which is also called a polygon data sets. So these are the basic representation of vectors. Now what happens is, in case of Earth observations analysis, most of the time we may be having these vector data sets. To create different segments, what we do, we need to carry out a conversion of these vector data sets into a features which may be considered to be a part of an image. So rather than having a line as an individual line, what may what we may do is that we can create a grids of horizontal and vertical lines, and within the each grid line a point can be placed, and based on the presence of any input features, so it may be like point, line or polygon, the corresponding grid can be marked and we can transfer the attribute to that grid. So like in this case, in the picture over here you are seeing that there are multiple data points. So each of these points on a vector point which we are having over here will actually fall in somewhere in the grid point on this place. So this particular grid as a whole box, square box which you see, can contain the attribute which is present in a point. Same is also true for line, but as you can see in the line, basically in the vector format we just keep the pointers or maybe a start and an end point, and we may assume that whenever a pair of start point and end point is being given, then there's a connectivity between these 2 points. That's what in the vector data format we assume. But when we take that line into a raster data format, then what happens is that all the places where, or all the grids where this line actually gets intersects with the grid locations, so all those grid locations are being marked and stating that this particular line belongs to basically, or this particular grid belongs to a line or not, so that can be marked. Same is also with the area, but in the area, as you know, that the boundary is being included, but also all the enclosed pixels, or basically a grid point which is present within an area is also getting marked in a raster format. So these two are actually a way of representing the data sets, and as we can see over here that the effect of the rasterization process is that whenever you put any point, it gets a kind of the linear feature no longer remains as smooth, so there will be a kind of Zagger effect. So as you can see, this is also called a staircase effect, which may be present in your raster mask data, which has been created from a vector data sets. So this is just one pitfall of rasterization process, and in our modeling approach we have to, or whenever we the mask based data sets when we create, so we have to keep in mind that this may be one of the source of the error. In case of area, if it is perfectly aligned, like in the case which is represented over here, then all the data points will fall within the grids, and this will have a perfect matching, and there won't be any staircase effect in your data sets. But if your polygon is not, or polygon basically the edges are not aligned horizontally or vertically, then in those cases what may happen is that you may be having at the boundaries of each of those area where we can have a staggered staircase effect, so that may be present. And all these raster vector data sets, we may be having a spatial reference. So generally that's the difference between the other image format like PNG or any other format which is being used. So in that case, there's no geospatial references. So means each of the point in a geospatial data set, you may be having a spatial references. So that also has to be present. So in EO data, you may be having a vector and raster data, but there are also an auxiliary informations which is present in terms of lat long, or maybe some parameter using which we can translate each of the locations in a form of raster and in a form of basically the lat long value. That's what we can create. So with this basic overview of EO data sets, we'll now see that what are the different applications which is existing in which can be used for AI applications. So this is just an example where different satellite images or imagery has been taken, and on each of those images there are different AI based algorithm has been executed to identify the different crop types. So like in this case we are having a 6 different crop types which is present. So from the satellite images we can look for any specific features which has been understood by a particular algorithms, and using that algorithms we can do a predictions, and then we can also identify the different stages of crop, and as well as different type of crop which can be used for identifying the different crop types. So that's what we can do it in using AI based applications. There are also a few of the applications which is present, especially which is not on the basis of the raster or grid data sets, but rather than in terms of connectivity, or we can also call it as a network or a connectivity graph based systems, where we can analyze the different segments of the road networks to identify that what are the places where the high volume traffic is existing, what are the places where low volume traffic is existing in a road networks, and so on. So for that we can create basically a GNN models. So it's basically a graphical based or graph theory based neural network models, using which we can compute the presence of any specific features on each of those nodes, and then we can come up with a certain conclusion, like if a lot of people are traveling from one place to the another place, and collecting that data sets and doing some graphical analysis, we can make a measurement that the place is actually some kind of entertainment place, or people are just going there for spending weekends, and so on. So those kind of analysis can be carried out with the help of basically the graph based data sets along with the raster data sets. The task which we are having in EO data set is, or generally in the classification, is one of the approach which we follow it in Earth observation areas. So there are multiple ways of identifying a particular type of class, or you can also consider that this to be a kind of category of a piece of land on Earth which has been basically extracted from a satellite imagery. So like in this case, you see that there are multiple image chips. So in this case, basically the data set consists of around 1500 different piece of images, which has been categorized into 4 groups. So each of these groups is having a 1500 images, and what the AI based model tries to do is that we have to identify each of these particular chips, that where this particular one particular piece of the image actually represents what as a whole. So in this case, the data set actually is your image input, and output will be actually a simply tag telling that this image is of which category. So that's the one way of doing the classification of your satellite image, where the whole image itself is being categorized by training models, and based on the input data set it can provide, and it can tell that it is of which category. So is it like a vegetation area, or a piece of land is actually sand, or is it a water, or so on. So those kind of things which we can do it. So in this case, chip as a whole is your input features, and corresponding attribute is a kind of a single layer. Then there's another task which is present in Earth observation. So that's basically called an image segmentations. So in this case, not only each of the pixel gets classified into one of the categories, but rather than within the category itself, you can have a count of very crisp boundaries. Like in this case, you see that there are different built-up area which has been identified using an basically a CNN models, which is nothing but a kind of modified, basically a modified CNN models, which is working on the transfer learning approach. So using those training models, which we can segregate, and we can create the different parts of the different objects present in an image. So generally in those cases, what we need to have is a very precise satellite imagery and the corresponding image labels. If your image labels are not in properly aligned format, then in that case there may be a discrepancies. So we need to have a proper and appropriate algorithms where we can create different object identified on a satellite imageries with its crisp boundary, and this whole process is called an image segmentation approach. So it uses the band informations or the spectral characteristic of the images along with the geometrical features of an object. Like object has to be a closed one. If it is not a closed object, then it means like it may be an open area and also distinguished area. So you see that there are different ways of identifying the crisp boundaries in the satellite images, and then that can be used for creating different models which can help us doing an image segmentations. So generally all these tasks, what we do is we take a raster data sets. So that raster data sets may be in satellite imageries where we may have multiple bands. So generally we have minimum 4 bands which are being given to us from any kind of data service provider. In some cases, like in Landsat, we may be having 8 or 9 channels, 8 channels basically, and giving the information about the different spectral range, like 250 or 340 nanometers or IR range and so on. So we can take those satellite imageries, and then based on the vector data sets, what we do, we create a kind of mask. So as we have seen earlier, we may be having a vector data which is a simple line polygons, simple line maybe or maybe a polygon features. Like in this case, we're trying to extract the linear features, that is not as an object boundaries, but as a length or or a linear feature which will having a length very high compared to the width of the images. So we carry out the vector to raster or the mask creation, so that rasterization process happens. So once we have that rasterization processes and the different raster data sets, then what we do is we create the small patches. So it means like in the whole image gets divided into small piece of the informations, and then each of these piece is going to represent a partial information about the whole scene. So the model, what it tries to do is it takes the location of all the images along with the label files or the mask which has been created to do a initial development of your models along with the testing. So these two tasks is being carried out under the training, validation, and testing phase. So if you are happy with that, then we can go ahead and we can use it that training models for classification. Like in this case, this is a FCN models, that is nothing but fully connected neural networks. And then this trained models can be used for generating the different metric like kappa accuracy or IOU score or F1 score or the precision, recall, all those scores that can be created. And based on that, we can evaluate the quality of the predictions which we have observed in a piece of images. So this is basically the basic steps which is being carried out across the classification processes. It may be a AI based, it may be a non-AI based, it may be a simple statistical based approach. In whichever approach you take, you will be having a data set which gets created from the images. So once we have these images created into small pieces, then each of those piece of images we try to extract the informations. So this is basically the steps. So we create especially in the case of linear features, we have to keep in mind a few of the things which may not be applicable in non-linear features. Non-linear feature means basically an topological object like full area, or it may be a point. So in compared to that, linear features basically has a unique challenges in terms of data inputs. So what happens is, like, whenever you create it into a multiple piece of the images, then what may happen is that at the edges of sub images there will be a kind of edge effect. So it means like this point, this whole chip will get created, and correspondingly there has to have some kind of additional input data to recover the whole semantic of this image. If you don't have it, then each piece of segment is actually working individually, and we will not get the interconnection between the multiple images. So in that case, any kind of ML task which is being represented over here as a kind of function transformation of this piece of image is going to give you basically the linear feature present in that piece of images. So like we may be having a road segment in this case, and that's what we are getting, it gets highlighted. So whenever the accuracy assessment happens, then at that time these labels pixels is being used for computing the effectiveness of training cases. And in case of linear features, wherever there is a different piece of information, and if that piece of information is voted overwhelmingly, so it means like on each of the pixel which is shared across or which maybe needs to will be neighbor to each other in each of those blocks. So they may be giving you a kind of informations on the edges. Those are called edge effects. So what we can do is we can combine all of these small piece of information, and wherever there is a high intensity information present, so that can be considered as one of the nodes. This is basically the way to extract the linear features. So linear feature is quite unique in terms of other features which is present in your on the earth. The reason for that is in the linear features can be, if it is viewed from different perspectives, so it can be considered as a polygon, like a road can be considered as a polygon, or maybe a line, and so on. So linear feature has to be taken, if you're not considering them to be a polygon rather than simple linear features. So in that case you have to consider it the effect of the breaking the images and then working on each piece of the images separately. So in this case, basically the total image is being segmented, and each of the segment piece is going to give you some kind of informations. Then on the edges or the places where two different chip meets and they have some kind of high intensity of the information present on those edges, then using that what we can do a complete recovery of these satellite images. So this is how there's a slight difference between the generic image analysis and the image analysis which we carry out using the on which we carry out on the satellite images. So satellite images needs to be considered piece by piece wheel basis, where in most of the other AI tasks related to image processing will have standard images of 1 into 128 or 256 into 256 and so on. So this is what we have to keep in mind, that in linear features we have to take care of a specific conditions. Yes, so this is basically the slide is which we are trying to showcase that generally there is a confusion between machine learning and CNN models and so on. So if you try to gather the information which is available in the open source, that is in Google and so on, then what happens is that we get a multiple definitions of ML, CNN and so on. And what are the differences? It becomes a very difficult task to understand. So this slide is basically providing you that information that in case of machine learning based classification scheme which is being applied, so you as a user or as a developer basically have to define the features which is expected to be present in an image. So for example, let's say if we were deciding a particular place like a lake identifications, and we know that any kind of lake which is calm is not going to reflect a very high amount of energy in the different spectral bands beyond the red. So in those cases, what may happen is that you have to look for a way to take the different spectral band and look for an information representation of taking the combination of different band and representing them as a single feature. So that feature may be nothing but a kind of quadruplet. So it means like the four. If you're using a list tree imagery, so you'll be having 4 bands. Now at a particular pixel locations, you will take all the 4 bands data sets, and that can be represented as a whole as one of the features. So that is nothing but a simple spectral vectors. Or it can, sometime what may happen is that a group of pixels which may not be basically linked with each other in a spatial domain. So it means like it is not necessary that 2 pixels which are close to each other present in an image will show the same amount of correlation in the spectral space or same amount of connectivity connection between different data sets. It is not necessary. So if you want to create, let's say, water body, so water body may be scattered in your scene. So all the water body will follow a slightly different approach of different values of the spectral bands. But as a whole, if you want to represent the water body, then what we can do, we can create an average vectors, and those vectors can be a representative of a particular class. So thus we see that we create a modeled vector representations, and then we have each of the input features, that is a quadruplet or 4-band input, which may be considered as one of the features. And once you create those features, then we basically pass on those features to a different classification scheme, ML-based classification scheme. And this is also the approach which is being used in traditional classification schemes. This is also called an offline data processing. The reason for that is that all the input data set, whatever you have, you are going to take it as an input and carry out the classification scheme. Where in case of CNN and DNN models, we don't bother about the feature extractions, but rather than all the expected features which is supposed to be present in an image will get extracted by the model itself, and it will store the information of that knowledge in form of collective weight, and that's how we create an ML basically and CNN based models, where the feature extraction and corresponding interlinking between those feature extraction, both of them are a part of models. And what we can do is, the next time whenever any input image is available, so we can use that basic model which is being presented to us, and we can carry out different tasks like object identifications, as we see in segmented images, or we can do a pixel by pixel classification. We can also label each of the satellite chip imagery using the CNN or DNN processes. So one of the fundamental approach to assess the performance of any kind of AI models is that you compute a few metrics. So most widely used metrics is basically a precision and recall. So precision basically talks about that if any basically a section or a part of the output which gets generated by the models in compared to the total. So in the precision models, what we do is we take the total number of output generated by a model, and out of which how many of them are actually correctly predicted. So if you take the ratio of these two, you get a precisions. Same way, total number of expected or as per the true value, how many objects has been identified correctly, and out of those total identifications, how many input objects has been given to the models. That's basically called a recall. A recall and precisions, we take a mean of or harmonic mean of these two values. That can also be used as one of the metric for F1 measures. So which takes care of the biasing. Like your models may be giving you a correct output, but for at a higher rate, but may not be for all of the objects and so on. So those basically is being that how these two recall and precision parameters are balanced, that is being given with respect to F1 score. For the object-based evaluation processes, again we do the same computations, like how many total objects get detected. So that's also called an overall accuracies along with the total objects. So in case of object-based models, what we do, we take a precision of overlap boundaries. As I was telling that earlier, that in case of object, we may be having a precise classification of each of the pixels bounded by a very crisp boundaries. So if you're having object-based classifications, then you use the same precision and recall, but in this case for each of the object level, not at the dataset level, but at the object level itself. So what portion of the total objects is actually overlapping, which is actually present, and what has been predicted by the models. And at the bottom we may be having an actual objects, total area of an actual object, or a total area of total predicted box. So that can also be used. So in that case, if you create another metric called IOU, so it basically talks about the overlapping area within the objects and the total area divided by total area defined by or enclosed by the object and as well as detected objects. So these are also the measures which is being used for doing an basically the measures. The another important factor which is being used in satellite imagery or image-based classifications for feature extraction is called basically the convolution approach. So convolution approach, what we do is you take the whole satellite imageries and then what you do, you take a defined boundaries generally enclosed by a rectangular box which may be a multiple of number of pixels. Like in this case, this animation is showing 5 pixels, so 5 by 5 pixels which we'll be having, and within that we try to create a kind of summarized view. So within the basically 5 by 5 pixel, we compute a summarized view. So it means all the 25 pixel is going to give us some information that can be replaced positions in a pixel. So that's what we do it over here. So you create a kind of approach where it provides you the neighborhood or a proximity effect which is generally being observed in any kind of spatial objects. So most of the spatial objects will have a very close relationship to its neighborhood. So it means like autocorrelation, especially the spatial autocorrelation values will be very high. So to take the effect of that in a measurement consideration for doing classifications or feature extractions, maybe manually or maybe the during the training case itself, convolutions can be used for that purpose. So this is just an example where convolutions which will be using it for doing an basically the image classifications. So with this actually we'll be ending today's session. So in today's session basically we talked about the different tasks which is possible on a EO data sets. There are few basic steps necessary to carry out an EO based classification or segmentation task. So for that, what are the things which we need? So we need to have a vector file or a raster file available to us if, in that case. And then there are few basic metrics which may be required. There's also a possibility that how we can combine or how we can look to handle the piecemeal approach, especially for the linear features where the number of pixels which is present in an output mask will be very less compared to the overall output window. So in that case, how we can take care of the neighborhood effect by taking the multiple overlap windows and looking for higher threshold combined values to recover the total features images. So these approaches which we should be aware of that in the next class onwards, basically based on these approaches we'll be solving and we'll be trying to do a few of the algorithm implementations. Okay, so if you have any questions, you can post those questions and we may be responding it to those questions in a couple of minutes. Thank you.